Welcome to APEC. It's April 17th, and I'm your moderator, Tim Ventura. I'd like to thank everyone for joining us on this call, along with everyone watching us on YouTube. In today's session, Michael Boyd will discuss UAPs and gravitomagnetism. Frank Milburn will be talking about UAPs and the Catalina Island incident. And Todd Desiato will present the derivation of gravity from the uncertainty principle. After that, we'll catch up with the latest research from the Falcon Space team, and we'll be wrapping up the event with open discussion and ad hoc presentations. A couple of quick reminders and then an announcement. You can view conference replays, details, and speaker info on our website at www.altpropulsion.com. Again, go to the website, check it out, share it with some friends. Please save your questions for the Q&A session after each presentation. Go ahead and type any of those questions that you have into chat. We'll go through them after each presenter finishes. I also want to mention as an announcement, we have an unconfirmed report that Mark McCandlish may have passed away on April 12th. Mark was a good friend. He was a really valuable part of our community, and we were honored to have him speak at APEC late last year. We're going to continue working to try and confirm this. And I hope that this is a mistake, but there is a legacy.com obituary notice for Mark McCandlish in Redding, California. We're just trying to confirm that this is the correct person. So on that note, let me introduce you to our first guest. Michael Boyd has an impressive 40-year career as an engineer and scientist, starting in 1982 at the Hughes Aircraft Company. His expertise has spanned component manufacturing, development engineering in the medical device, microelectronics, telecommunications, semi-conductor, and hard drive industries. Michael has a BA in physics from UCSBM and has published research in numerous technical publications, including the International Society for Optical Engineering, the National Institute of Standards and Technology, and the Journal of Vacuum Science Technology. So Michael, welcome, sir. It looks like you're already unmuted. Okay, let me hand it over to you.
Hello, everyone. Thank you for this opportunity to present some of my research today. I'm feeling pretty stoked about it. What I'm going to start off with is I want to talk about, basically I have 3 jobs. And one of the jobs is I'm a physicist, I'm an engineer, and more recently I'm an archaeologist. And as an archaeologist, basically what archaeologists do today, it's not like Indiana Jones. It's more like being a construction worker, except that you don't actually do any work unless you find something. And so, for example, I have my hard hat here that I'm showing, and what I have is these stickers here from different tribes, because when I'm monitoring what I'm doing, if you look at my image, I don't know if you guys can see it because I'm in the share mode, but if you can see my image, I have this yellow hard hat, and it has these stickers. So one of them says Yosho Dishi, and the other one says Essalon. And so when they're digging in an area that's sensitive, they have to look out. They have to look out for resources, maybe a burial from a prehistoric burial from the past from one of the tribes. And one of the problems that you run into is there's a cultural difference between the tribal groups and the archaeologists and the construction workers. So because of that, I had to learn about what's called nonviolent communication. Essentially, when our culture is basically built on this system of what I call reward and punishment. It's built on violence. So basically, if you're good, you get rewarded. If you're bad, you get punished. But in most other species, let us say, it's more built on on empathy, because you depend on each other's for your survival more. And because of what happened with agriculture, basically back in the past, there was what was called the agricultural revolution. And that created where we had haves and have-nots. The people that had food, they were the haves, and the people that didn't, they were lesser humans, okay? And we like to categorize, and that's created what's also called intergenerational trauma. So we learn how to deal with stress from our parents, who learned it from their parents, and so on and so forth. And it's all built throughout our culture, throughout the world, on this system of reward and punishment. And what nonviolent communication is about is love. It's about compassion for each other. It's really, I think if there's any extraterrestrials or whatever out there, that they're afraid of us because we're so violent and our culture is so violent. And if we could learn nonviolent communication, well, maybe they'd be more comfortable with communicating with us. Right now, I don't really see any reason why they would want to be. So, but in any case, nonviolent communication is essentially expression is about you, and empathy is about others. And there's basically 4 principles. There's observation without judgment. There's feelings. How does it make you feel? There's needs. Well, you feel this way because you need something. And then there's requests without judgment. Now, I personally have the most problem with the judgment part. Okay, the without judgment is difficult for me. And I think that's because of our culture. But so I just wanted to first introduce you to this idea of nonviolent communication. Now, what I'm going to do here is I'm going to talk a little bit about my my job experience and how it's relevant to this. But first, if you look up here in the top, you'll see there's this link here to my that's to my CV, and I'm going to open that up. Let's see if you guys write that down, you can. What I'm going to do, the reason I'm opening this is I want to show you first, if you don't have your CV on this website, it's something you might consider. And then also I want to show you how it works, because it's a little different from most in that it has, it's real basic, but then there's a tab to pull down. And if it ever opens, maybe, oh, here we go.
Yeah, well, and Michael, I hate to interject, but we're getting to be about 12, 13 minutes in. So,
oh, okay, I'll make this rapid. I don't even know if it's going to work. So, let's skip. Okay, so what you hear, this is the relevant, what I thought was relevant. I worked in Santa Barbara Research Center 1982 to 91 as a senior development engineer, fabricating these infrared detectors like you're seeing when you're watching the UAP imagery, like FLIR-1 is a detector device that I probably helped fabricate. And then I got a job in place which was an environmental test lab. So I broke stuff for a living. That was kind of a fun job. And then in 96, 98, I got a job for this test equipment manufacturer for hard drives. And that's where I first discovered gravitomagnetism. then below that, I have some of my patents. You can see the most recent one in 2019 is a device and method to generate and capture of gravitomagnetic energy. So enough about me. And this, I just thought was kind of funny. It kind of reflects how I feel about academia, let us say. And basically what it says, along with antimatter and dark matter, we've recently discovered the existence of doesn't matter, which appears to have no effect on the universe whatever. So, I mean, what I'm trying to show is that I'm not necessarily right. I mean, I'm just, hopefully my guesses are just more educated. So now what I have here is I'm going to talk about semiconductor diode physics. And this includes a little video here about that discusses how they work. A diode is a semiconductor material with a PN junction connected to two electrical terminals. The P side of the junction has an excess of protons called holes and also called acceptors. The N side of the junction has an excess of electrons called donors.
Junction diode, properties and uses. Formation of the PN junction. The P-type semiconductor has an excess number of holes. Therefore, holes are the majority carriers of charge in P-type semiconductors, as shown. Similarly, N-type semiconductors has an excess number of electrons. Therefore, electrons are the majority carriers of charge in N-type semiconductors, as shown. The combination of P-type and N-type semiconductors results in a junction. This combination has many applications in electronic devices. When a P-type semiconductor is suitably joined to an N-type semiconductor, a contact is established between them and is called a PN junction. Formation of depletion region. The PN junction formed out of the P-type and N-type semiconductor separates P-type semiconductors from the N-type semiconductors. However, because of the contact, some of the electrons from the N side enter the P side. Similarly, some of the holes from the P side enter into the N side. So at the junction, these electrons and holes combine with each other. The hole and electron neutralize each other on such recombination as shown. Therefore, in the region close to the junction, only negative ions are left behind on the P side and only positive ions on the N side. This results in the formation of a narrow charged region on either side of the PN junction. The N-type semiconductor close to the junction becomes positively charged, and the P-type semiconductor close to the junction becomes negatively charged. On either side of the junction, the region D becomes free from mobile charge carriers.
The region D is an event horizon.
On the N-type side of D, no free electrons exist, and the P-type side of D, no holes exist. In the region of D, only immobile donor and acceptor ions exist. The region close to the PN junction is depleted of mobile charge carriers and is called the depletion region. Since on either side of the junction J, stationary positive and negative charges exist, there is an electric potential difference of VD between the edges of 1 and 2 of D. This potential difference VD across the junction is called the potential barrier, as it prevents further movement of holes and electrons.
Now that region D is important because that's, or the potential barrier as it's called, is we'll talk about that more later because that's what we're talking, the barrier we're talking about when we're talking about what's called quantum tunneling or the tunneling effect. So now what I have here is a design specification drawing for my invention, the mass spin valve. This is the head disc assembly. And what you'll see here is on the left here is a pattern of nanobumps and nanopits. this top region is nanobumps. And it's like the top, there's a 40 micrometer times 40 micrometer square nanobump. And that's at 1.8 inches. And then a radius. And then at 1.45 inches, at that radius distance is 40 micron by 40 micron nano pit. And so what I did is I made nanobumps and nanopits with a device called a focused ion beam, which essentially is an electron microscope, but instead of using electrons, it uses ions. To remove material, I used a beryllium ion. To deposit bumps, I used a tungsten ion. I picked tungsten because it's anti-ferromagnetic material. So it shouldn't be, it's kind of like aluminum. You can't magnetize it. And then over here on the right is the disc. And then there's this little device called a slider. It's called a slider because it looks kind of like a sled. And here's a representation of a side view of the slider. The disc is spinning counterclockwise at 500 inches per second. It's roughly 27 miles an hour. And then if you look here, I have two sensors on my device. I have a giant magnetoresistor, which is this little tiny region on the bottom of the slider. And that's a special resistor that's sensitive to changing magnetic fields. On the top of the slider, I have a thing called a piezoelectric crystal. And what that is a crystal, if you tap it, it produces a voltage signal. And so basically I use one to measure the magnetic force or the magnetic field strength, and the other I use to measure the physical motion of the slider. The slider, like you can see, is a little arm that's sitting over the disc as it's spinning. Now this is, I'm not going to spend a lot of time on this, but this is basically examples of my test stand. On the right is what's called a spin stand, and it contains a thing called a spindle, which turns the disc, and then there's, like, on the left you can see more details there. I have like the actuator arm. I show where the head is. Up here on the top left, I show some of the circuitry, the basic circuitry involved in it. But essentially, this is a representation of the test bed. And you'll notice over here on the left, there's a little note, floppy drive. Now, how many people still use floppy drives? That just shows the antiquity of this. So now let's get into the physics of nanogravity. Gravitation is slower than the speed of light in the context of frame dragging. Examine the difference between gravitomagnetic induction and electromagnetic induction. A GMR read head is observed from a 10 micron by 10 micron square bump of around 32 nanometer tall on a hard disk platen, spinning at a constant linear velocity of 500 inches per second. The disk is spinning counterclockwise. So we observe the first electromagnetic induction signal on the left under the GMR sensor. The upward magnetic induction is induced by a 90-degree change in the angle of the edge of the bump at the speed of light. This is followed by a downward gravitomagnetic signal of a bump 1 microsecond later, traveling at the speed of gravity. We observe the downward polarity second electromagnetic, this little pulse here, signal that's on the right of the gravitomagnetic signal as the square nanobump moves under the GMR sensor 0.8 of a microsecond later, traveling at the speed of light. In this example, we observe the gravitational frame dragging is 1 microsecond, which is this time difference between the first pulse and the gravitomagnetic signal. Voltage is in millivolts. presence of matter moving produces a pull force and a negative polarity gravitomagnetism. This image is a cross-sectional view of the GMR reed head with a piezoelectric crystal mounted on the backside of the head slider. The GMR reed head is sensitive to magnetic field changes, while the piezoelectric crystal on the back of the slider is sensitive to the physical motion of the head slider. A 10 micron by 10 micron square bump of around 32 nanometers height measured results are shown. On the left, below the cross section, is the piezoelectric glide head signal, where we observe an undampened physical pull against the head slider against the force of gravity as shown. I have the force of gravity is down here relative to the slider. On the, hold on, I lost myself. On the right, the GMR sensor shows a negative polarity gravitomagnetism. And I skipped some. On the left is, okay, on the right, sorry. This infers the presence of matter on the spinning disk produces a physical pull force and a negative polarity gravitomagnetism. In this example, we observe the gravitational frame dragging is again 1 microsecond. The absence of matter moving produces a push force and a positive polarity gravitomagnetism. The image is a cross-sectional view of the GMR reed head with a piezoelectric crystal mounted on the back of the side of the head slider with a nanopit on the surface of the disk. A 10 micron by 10 micron square pit of around 52 nanometers depth measurement results are shown. On the left is the piezoelectric glide head signal, where is observed a short dampened physical force, push force against the head slider, against the force of Earth gravity. On the right, the GMR sensor shows a positive polarity gravitomagnetic signal. This infers the absence of matter on the spinning disk produced a push force and a positive polarity gravitomagnetism. In this example, we observe the gravitational frame dragging is again 1 microsecond. This also infers there exist 2 different time frames, one for matter, or the lack thereof, and another for electromagnetism, or EM. Context of space-time moving relative to the GMR sensor. So we have, these are 2 AFM micrographs of the nano bump in the nano pit that I'm showing data from. Atomic force microscope is a device that it's a little nano-sized lever, kind of like the head sits on, but it has a little sharp tip on the end of it. And on the back back of it is one of these little these piezoelectric crystals that goes back and forth. And there's a laser that shines on the tip of the thing, and as it moves, it measures atomic force by using fringes that are measured with a laser, essentially. And it's a way, it's also, if you take that little tip and you coat it with a magnetic material, you can make what's called a magnetic force microscope, which is what I did to calibrate my measurements. So above are the 3D images that were taken with what's called a Park Systems atomic force microscope. And you can see that's where I got the 52 nanometer depth and the 32 nanometer height, as I measured it and so what my hypothesis is, as the pit goes by the GMR sensor and the force sensor, it's creating expanded space-time because the distance away is only 100 nanometers. It's really close. And the bump it's the opposite. It's denser space-time. So and what's going on is we have a change in medium. between denser and expanded space-time. We exist in something in between those two. Now, I took all that data, like I showed you at the beginning, from the nanopit disk, and then I normalized it to the magnetic force microscope data. So I could take the peak signal of the GMR readback and say, okay, 1 volt, 1 nanonewton force is equal to 1 volt of readback signal as calibrated from that MFM measurement. And so what I did is that then I take my data and I put it into this plot of force, which is the x-axis, versus volume, which is the y-axis. And that's when I discovered that what I had was a gravitational junction. So by varying the area of the nanopits and the nanobumps on the surface of the spinning disk, the graph of the measured gravitational forces derived from the gravitomagnetic induction signals recorded. A gravitational diode curve is observed for variable area pits and bumps. The P side of the gravitational diode is the acceptor side of the junction, producing positive gravitational induction and a push force, which you can see over here in this area, which is a third order polynomial of a hyperbolic force, like that of a balloon. Now, this is important, this balloon you'll see later when we start talking about UAPs. The N side of the gravitational diode is the donor side of the junction, producing negative gravitational induction and a pull force with a second order polynomial of a parabolic like normal gravity. Normal gravity is a parabolic. Now we're going to talk a little bit about gravitation is faster than the speed of light in the context of quantum tunneling. Tim, how's my time?
Oh, so just about halfway there, but if you run over, that's fine because we've got a long Q&A session.
Okay, cool. Okay, so so in the barriers where this entanglement, the barrier is this part in the middle. And in the barriers where the entanglement occurs, but the protons don't really move. They don't go anywhere. They vibrate. You might say they sing and dance to the same tune. Quantum tunneling is an example of a quantum entanglement phenomenon. Quantum tunneling is the quantum mechanical phenomenon where a subatomic particle passes through a potential barrier, again, e.g. an event horizon, instantaneously. The hypothesis is that matter, e.g. mass or gravitons, as having properties of both waves and particles. Notice again, this is a type of event horizon. So when we talk about a barrier, we're talking about an event horizon. Now I have this little video that I found, which I think is really excellent in explaining how quantum tunneling works. But the important thing I want you to notice, pay attention to, is there's the signal that gets through the barrier. One hypothesis is this is what's called a pilot wave. And it's essentially, the hypothesis is we're back from the future. Time is retrocausal. So the future is pushing back. And if you watch this closely, you'll notice that she talks at the end about this phenomenon.
Have you heard that quantum mechanics is impossible to understand? You know what? That's what I was told too when I was a student. But 20 years later, I think the reason so many people believe one cannot understand quantum mechanics is that they are constantly being told they can't understand it. But if you spend some time with quantum mechanics, it's not remotely as strange and weird as they say. The strangeness only comes in when you try to interpret what it all means. And there's no better way to illustrate this than the tunnel effect, which is what we will talk about today. Before we can talk about tunneling, I want to quickly remind you of some general properties of wave functions, because otherwise nothing I say will make sense. The key feature of quantum mechanics is that we cannot predict the outcome of a measurement. We can only predict the probability of getting a particular outcome. For this, we describe the system we are observing, for example, a particle, by a wave function, usually denoted by the Greek letter psi. The wave function takes on complex values, and probabilities can be calculated from it by taking the absolute square. But how to calculate probabilities is only part of what it takes to do quantum mechanics. We also need to know how the wave function changes in time, and we calculate this with the Schrödinger equation. To use the Schrödinger equation, you need to know what kind of particle you want to describe and what the particle interacts with. This information goes into this thing labeled H, which physicists call the Hamiltonian. To give you an idea for how this works, let us look at the simplest possible case. That's a massive particle without spin that moves in one dimension without any interaction. In this case, the Hamiltonian merely has a kinetic part, which is just the second derivative in the direction the particle travels, divided by twice the mass of the particle. I have called the direction x and the mass m. If you had a particle without quantum behavior, a classical particle, as physicists say, that didn't interact with anything, it would simply move at a constant velocity. What happens for a quantum particle? Suppose that initially you know the position of the particle fairly well, so the probability distribution is peaked. I have plotted here an example. Now, if you solve the Schrödinger equation for this initial distribution, what happens is the following. The peak of the probability distribution is moving at constant velocity. That's the same as for the classical particle, but the width of the distribution is increasing. It's smearing out. Why is that? That's the uncertainty principle. You initially knew the position of the particle quite well. But because of the uncertainty principle, this means you did not know its momentum very well. So there are parts of this wave function that have a somewhat larger momentum than the average, and therefore a larger velocity, and they run ahead. And then there are some which have a somewhat lower momentum and a smaller velocity, and they lag behind. So the distribution runs apart. This behavior is called dispersion. Now, the tunnel effect describes what happens if a quantum particle hits an obstacle. Again, let us first look at what happens with a non-quantum particle. Suppose you shoot a ball in the direction of a wall at a fixed angle. If the kinetic energy or the initial velocity is large enough, it will make it to the other side. But if the kinetic energy is too small, the ball will bounce off and come back. And there is a threshold energy that separates the two possibilities. What happens if you do the same with a quantum particle? This problem is commonly described by using a potential wall. I have to warn you that a potential wall is in general not actually a wall in the sense that it is not made of bricks or something. It is instead just generally a barrier for which a classical particle would have to have an energy above a certain threshold. So it's kind of like in the example I just showed with the classical particle crossing over an actual wall. But that's really just an analogy that I have used for the purpose of visualization. Mathematically, a potential wall is just a step function that's zero everywhere except in a finite interval. You then add this potential wall as a function to the Hamiltonian of the Schrödinger equation. Now that we have the equation in place, let us look at what the quantum particle does when it hits the wall. For this, I have numerically integrated the Schrödinger equation I just showed you. The following animations are slow motion compared to the earlier one, which is why you cannot see that the wave function smears out. It still does. It's just so little that you have to look very closely to see it. I did this because it makes it easier to see what else is happening. Again, what I have plotted here is the probability distribution for the position of the particle. We will first look at the case when the energy of the quantum particle is much higher than the potential wall. As you can see, not much happens. The quantum particle goes through the barrier, it just gets a few ripples. Next, we look at the case where the energy barrier of the potential wall is much, much higher than the energy of the particle. As you can see, it bounces off and comes back. This is very similar to the classical case. The most interesting case is when the energy of the particle is smaller than the potential wall, but the potential wall is not extremely much higher. In this case, a classical particle would just bounce back. In the quantum case, what happens is this. As you can see, part of the wave function makes it through to the other side, even though it's energetically forbidden. And there is a remaining part that bounces back. Let me show you this again. Now remember that the wave function tells you what the probability is for something to happen. So what this means is that if you shoot a particle at a wall, then quantum effects allow the particle to sometimes make it to the other side when this should actually be impossible. The particle tunnels through the wall. That's the tunnel effect. I hope that these little animations have convinced you that if you actually do the calculation, then tunneling is half as weird as they say. It just means that a quantum particle can do some things that a classical particle can't do. But wait, I forgot to tell you something. Here you see the solutions to the Schrödinger equation with and without the potential wall, but for otherwise identical particles with identical energy and momentum. Let us stop this here. If you compare the position of the two peaks, the one that tunneled and the one that never saw a wall, then the peak of the tunneled part of the wave function has traveled a larger distance in the same time. If the particle was traveling at or very close by the speed of light, then the peak of the tunneled part of the wave function seems to have moved faster than the speed of light. Whoops, what is happening? Well, this is where the probabilistic interpretation of quantum mechanics comes to haunt you. If you look at where the faster than light particles came from in the initial wave function, then you find that they were the ones which had a head start at the beginning. Because remember, the particles did not all start from exactly the same place. They had an uncertainty in the distribution. Then again, if the wave function really describes single particles, as most physicists today believe it does, then this explanation makes no sense. Because then only looking at parts of the wave function is just not an allowed way to define the particle's time of travel. So then how do you define the time?
So to simplify David Bohm's hypothesis, there is evidence for a pilot wave and it's pushing back. It's pushy. So how else do you get something from empty space? So that kind of leads to what I call the postulate for the theory of everything. I was going to use a Sharpie and put this on my big toe, but then I looked at my toe and decided that might not be a good idea. And I went with this instead. So the postulate of theory of everything is gravity is a property of matter, but not a property of electromagnetism. The hypothesis is that protons, what are called holes in the semiconductor junction, and all forms of matter in their presence in our location in the universe, this is the source of the attractive force of gravity in the vicinity of matter. The other novel thing is the absence of matter produced a repulsive anti-gravity force that is much weaker than gravity force in balloon light. Electrons, however, do not contribute enough mass to really affect gravitation in any significant way. The geometry of matter, or the lack thereof, caused a force field to be produced so that I could measure. Now I'm going to talk a little bit on black holes, general relativity, and special relativity, GR and SR. Excuse me. General relativity GR is the theory of gravitation that was developed by Albert Einstein between 1907 and 1915. According to general relativity, the observed gravitational attraction between masses, something happened. Sorry. According to general relativity, the observed gravitational attraction between masses results from the warping of space-time and time by those masses. General relativity is developed into an essential tool in modern astrophysics. It provides the foundation for the current understanding of black holes, regions of space where gravitational attraction is so strong that not even light can escape. Okay, this next paragraph I'm stumped at. I don't know how to say this word in German. So I'm gonna skip it and say Einstein's On the Electrodynamics of Moving Bodies was received on the 30 June 1905 and published 26 September of the same year. It reconciles Maxwell's equations for electricity and magnetism with the laws of mechanics by introducing major changes in mechanics close to the speed of light. This later became known as Einstein's special theory of relativity. Consequences of this time-space frame of moving body appearing to slow down and contract in the direction of motion when measured in the frame of the observer. This paper also argued the idea of a luminiferous ether, one of the leading theoretical entities in physics at the time, was superfluous. There's still a lot of controversy over that one. The manifold of events in space-time is a substance. This has also been called what's in philosophy space-time substantialism. Einstein focused too much on the speed of light and not enough on the holes all around him. That's where the gravitation is. That electromagnetism is in space-time IA, let's call that EM space-time. And this is what Einstein's On the Electrodynamics of Moving Bodies describes, which reconciles Maxwell's equations for electricity and magnetism with the laws of mechanics by, again, introducing these changes to mechanics close to the speed of light. This later became known as Einstein's theory of special relativity, SR. And then if you look below here, I have in fine print, unfortunately, and it's in German, all the links, all the papers that I'm referencing the actual papers here for you. That gravitation is in space-time B, let's call that space-time B general G space-time. And that's what Einstein's general relativity GR describes. According to general relativity, the observed gravitational attraction between masses results from, quote, warping of space and time by those masses. When I write about this manifold of events in space-time, our substance, which exists independently of the matter within it, this manifold of events in space-time is the property that makes time as we measure it the emergent positive arrow of time. Therefore, time is a vector whose direction depends on your position in our universe, which is created by a change in energy states between gravitation to electromagnetism and vice versa. Okay, now what I'm going to do is show some examples of natural gravitational diodes. It's not basically this is something I believe is just part of nature, and so I have 4 examples of this. The first is what's called ATP synthase. It's what powers life. It takes protons and it uses the spin of protons to create power in the cell. The second is positive terrestrial lightning in the form of elves, blue jets, and sprites. The third is solar flares. The relationship between the time it takes for the solar flare to hit the Earth, about 7 minutes, and the coronal mass ejection to reach the Earth 2 to 3 days later. But there's also we've also find an example of this later, which I talk about, of how that there's a pre-signal, or like we saw with the tunnel diode. It goes on with the CME as well. The fourth thing is a supermassive black hole centered local universe, which is sort of my hypothesis. So do protons power life on Earth? In the semiconductor, the flow of protons is known as hole flow, while the flow of electrons is known as an electron flow. It's because of the movement of protons, or holes, that ATP synthase powers everything. That's alive on Earth. Animal, vegetable, even fungi have ATP synthase. This image here on the left is a live ATP synthase. The scale here is about 100 microns. So that little ATP synthase is rather small. A postulate is gravity produced by the spin of protons is the basis of all life on Earth, using this gravitational motor using protons. Power protein motors in every cell on this planet. I have this little video of ATP synthase represented through human motion. The molecular motor moves protons, which are here shown by H+, the power plant in the cell. Now, a few things to note. In this case, there's a barrier too, and it's a membrane. And it's an event horizon, and it's in your cell. And this is what it looks like using human motion. You'll notice at the end here, it spins backwards. I think that's cool. Okay, next, let's talk about positive terrestrial lightning in the form of blue jets, sprites, elves, and accelerated protons. Now, here we see a blue jet, and it's going up to like an altitude of 50 kilometers. Here we see sprites, which are going up to like 90, 80, 90 kilometers. And then elves, they'll circle. And those are up at around 100 kilometers. Now, typically you'll see the elves first, and they don't talk about elves in this little short, but you'll see the elf, and then you'll see some blue jets.
A view from above is helping scientists figure out how blue jets are born.
See
this
the elf?
Is a visualization of one over the Pacific ocean. Blue jets are like lightning, but they shoot straight up from storm clouds into the stratosphere. The gases there give the lightning its blue color. But it's the flashes that appear before the blue jet that have scientists excited. They think these flashes somehow cause blue jets. But what causes the flashes is still a mystery.
So my hypothesis is blue jets are expanded space-time or an anti-gravity representation electromagnetically. So something's pushing up. Next are sprites, which are also a form of positive lightning. And this little video is about
This
that.
is an incredible video of a sprite. Now, sprites have been captured on film and images a lot in the history of humanity or modern man, but they've never been captured with a 10,000 frames per second camera on video like this. And you can really see it's an incredible sight. And it was captured in Japan. And what a sprite is it's basically an electromagnetic charge that's up in the upper atmosphere above a lightning storm. And so what this is going to allow for is researchers to look at this video and maybe, you know, use this technique to capture more sprites in the future and learn how a sprite affects lightning and how a sprite is created and what causes it. It's really incredible. There have been pictures of sprites, video of sprites taken from way above from the International Space Station before, but again, never in this detail. And you can just really see its beauty and its power and the fact that that is definitely something that neither you nor I has ever seen before. This is an incredible video of a sprite. Oh. Now, sprites have been captured.
Looks like it started again. So the next thing is this relationship between a solar flare and a coronal mass ejection. A solar flare isn't just an explosion of hot gases. It pushes out waves of light at the speed of light. That includes light we can't see, including radiation in the form of X-rays and gamma rays. But another solar event called a coronal mass ejection can cause serious problems for electrical systems on Earth. During a CME, the fluctuations in the sun's magnetic field cause a large portion of the surface of the sun to expand rapidly, ejecting billions of tons of particles out into space. Unlike a solar flare, a CME doesn't produce intense light, but it does produce a magnetic shock wave that extends billions of miles out into space. It takes days to reach Earth as compared to 7 minutes for a solar flare. If the Earth is in the path of the shock wave, our planet's magnetic field will react to the event, and the magnetic shock wave from the sun will cause the alignment of the Earth's magnetic field to shift unpredictably. So besides the proton and its bigger sister, the black hole, the mass spin valve or gravitational rectifier occurs in the relationship between the solar flare, photons of EM, and the coronal mass ejection, ECME, gravitation, that follows showering the Earth and sun's proton flux. Now, interestingly, solar flares are known to affect the radioactive decay rate, it turns out. And then there's this article that I found that talks about it, the strange case of solar flares and radioactive elements. On December 13, 2006, the sun itself provided a crucial clue. When a solar flare sent a stream of particles and radiation towards Earth, Purdue nuclear engineer Ger Jenkins, who measured the decay rate of magnesium-54, a short-lived isotope used in medical diagnostics, noticed the rate dropped slightly during the flare, a decrease that started about a day and a half before the solar flare. This is an example of the sun's anti-gravity pre-signal, back from the future again. And here's a little video about that.
Thunderbolts project at thunderbolts.info. For many years, a scientific controversy has been brewing far from the spotlight of mainstream media. How constant are physical constants? For decades, the scientific consensus has been that true constants, such as the speed of light and the gravitational force, remain unchanged over time. But in recent years, more and more evidence has challenged this assumption. A telling example is now posed by observed changes in supposedly constant radioactive decay rates in relation to solar flares.
In 1904, Ernest Rutherford wrote the book, Literally, on radioactive decay. In this book, he states, in no uncertain terms, the constancy of the rates of radioactive decay. This allegation was initially shown to be consistent with experiment, and so was generally accepted, not to be double-checked for another 8 decades. It was only 3 decades ago that a rogue experimenter from Brookhaven National Labs published the results of a 4-year study into the decay rates of silicon-32 and chlorine-36. His results were astonishing. He found a seasonal variation of about 0.1% in silicon and about 0.3% in chlorine, in addition to a monthly variation. Physicists of the day were not amused. How could radioactive decay rates, long known to be constants, possibly vary?
At present, physics has no mechanism for radioactive decay. It's just a probabilistic theory. And very early in the piece, when Ernest Rutherford said the decay rates appear to be constant, this was taken as a license for geologists in particular who've been looking for means to date the age of the Earth to suddenly register geology as a hard science instead of a descriptive science like geography. And ever since that time, any anomalies in decay rates and so on have tended to be swept aside.
The Brookhaven National Labs report caused a small yet intense splash at the time, but discussion on the topic ceased for the next 12 years, and they were largely forgotten. In 1998, the PTB in Germany broke the silence by announcing the results of a 15-year study. Seasonal and monthly variation was confirmed in radium-226. Only 3 years later, Falkenberg announced a seasonal 0.37% variation in hydrogen-3. As if the announcement of annual and monthly cycles weren't enough, nature had yet another surprise in store for a pair of Purdue researchers. While searching for new methods of random number generation via nuclear decay, Jenkins and Fishback recorded 3 drops in manganese-54 counts of about 0.1%, corresponding with the 3 December 2006 solar flares.
One of the effects that was discovered was on the night side of the Earth, the radioactive decay decreased roughly a day before a flare appeared on the sun. And this effect was noted a number of times, so it was reproducible. The question then was, how do we get an effect happening on the other side of the Earth, on the night side of the Earth, away from the sun, being registered through the Earth?
The Purdue researchers who discovered this correlation initially tried to avoid speculating about this problem and published just the correlation, but their submission was rejected on the grounds that there was no known mechanism for radioactive decay counts to decrease in anticipation of a solar flare. Being forced to come up with a mechanism, they were later able to publish a paper where they suggest that a massive increase in solar neutrino production prior to the flare is responsible for the decreased counts. The reasoning is that the neutrino weakly interacts, and beta decay is via the weak force. Unfortunately for that theory, it was already established in 1998 that variation is present in substances which alpha decay, which is via the strong force. Neutrinos can't be the effector. So are there better explanations to be had in an electric universe?
The point is that all matter is connected in the universe. All of this suggests that it is much simpler than the neutrinos. It is this direct connection between all matter in the universe. And if quantum theory is telling us anything at all, it's telling us that it's due to resonant effects in matter, so that the atoms that are disturbed on the sun leading up to a solar flare, that disturbance, that change in the resonance of those atoms is available to radioactive atoms on Earth. In other words, this direct connection can invoke a change in decay rate. And this appears to be what's going on. And when it comes to quantum resonance effects, it also suggests, and this has been borne out by some experiments which have been forgotten about, and that is that low-frequency electromagnetic resonances would induce changes in radioactive decay. So what we're looking at there is being able to influence the dance of the nucleus, if you like, by sending in a signal which beats with that nucleus. And in the process can either increase the instability, that is, increase the radioactive decay rate, or slow it down, depending on the interaction. It does give us the opportunity of thinking about getting rid of radioactive waste in a more sensible and simple fashion than trying to bury it. This means many things to science. It means that quantum theory...
Well, now let's go to some evidence for central black hole universe. The black hole is a type of mass spin valve or gravitational rectifier, which is best described as a gravitational equivalent of a semiconductor junction, a gravity diode. The technical description is what's called a Maxwell's demon in thermodynamics. It's called that because it violates the second law of thermodynamics, i.e. entropy. Now, this is some evidence for a central black hole. These two perfectly concentric Einstein rings in the universe's electromagnetic microwave cosmic background, as reported by Sir Penrose in 2010, shows we exist in the jet of a supermassive black hole. Otherwise, we wouldn't see them at all. If we were off to the edge, we'd only see part of it. And the source of the paper, the Penrose paper is at the bottom of the page here. I've included the link. Supermassive black hole centered local universe. Space-time is a substance that flows, and in a certain reference frame, a black hole's jet, it expands to an outer event horizon, and in others, moving towards the black hole's inner event horizon, it contracts. We assume there's no zero time. Time as a direction, and space-time is dynamic, always moving inward or outward, depending on your frame of reference. Now, this image source I have here is a video called Cosmography of the Local Universe at 14 minutes and 20 seconds into the video. And there's a link there to the bottom. It's a real short one. The image of our local universe above shows that space-time is a substance and our universe is a gravity diode. It flows from the past, shown on the left, and into the future, shown on the right, and back again. The region on the left is denser space-time. The region on the right is expanded space-time. The expanded space-time region is actually pushing back against the past. This suggests that our region of space-time is a superposition of the past, denser space-time, and the future, expanded space-time in the here and now. Wait a second. So now I'm going to take and try and connect this all together for you. Okay, let's just focus a little bit about this slide. So what I did is I took this table out of Hal's paper, And basically the hypothesis is this: denser space-time, in denser space-time, which is like a typical stellar mass. So say we're on the sun. Time gets slower. I mean, time slows, but length gets shorter. And that's a gravitational effect. So, I mean, when you're on Earth and you're using your GPS, the GPS has to correct for the fact that the satellite in orbit, time is faster up there than it is down here. Because on Earth, we're in this gravity well. Now, expanded time is the opposite of that. It's where, think of like emptiness, okay? Time, think of the protons are like moving farther apart for the same area. And that expanded time shrinks, length dilates, and that's where you have this pushy anti-gravity effect. So if you look over here at his table, he describes that. He has on the top here variables, the stellar mass, typical stellar, and the space-time engineering metric. Space-time is where you're creating expanded space-time, which is what I think is going on with the Tic Tac. So basically, in one case, time slows, in one case, time's faster, in one case, length stretches, in one case, length shrinks. So now I was talking to Hal a little bit about, I was exploring time travel in the discussion with Hal. Let's assume the speed of light is our fixed time reference. We'll call that t equals 0 on the right. That's our first electromagnetic pulse. Let's assume that that's fixed. That doesn't change, whatever the reference rate, whether expanded or dense or space-time. With expanded space-time, time shrinks and length dilates. So an anti-gravity pre-signal would signal. We observed this effect for our 10 micron square nanopit. As shown, you can see there's this pre-signal here. Right there. Likewise with denser space-time, with our nanobump. Time dilates, length shrinks. So a post-signal would be observed. We observe that effect here with our nanobump nanopits. Now this is where we get into the Tic Tac space-time metric engineering GR effects. Greater G-force means times dilates, length shrinks, gravitational energy, while lower G-force means time shrinks, length dilates, anti-gravitational energy. This is based on the principles of general relativities, Einstein's theory of geometric gravitation, and the data. Now what we have here above is some frames I captured from the Tic Tac video from the Navy. And you'll notice that over here, this is an important number to pay attention to. This is the magnification. Most of these effects that I observed were at the magnification of 1. At 2, the infrared sensor's field of view decreases, and the bandwidth or the spectral characteristics change too. So now what I'm going to do here is, using my data and Hal's hypotheses, I'm going to try and explain what we're seeing here. You'll notice over here, there's on this top, that's our balloon, our anti-gravity balloon. We're going to drill down on some of these other things. Over here is an area where it's brighter. That means there's denser space-time there. Over here, this anti-gravity region is expanded space-time. Over here on the left, This region is also expanded space-time. Then we have this kind of interesting region where it's kind of a mixture of the two. In your junction, in your semiconductor junction, in the depletion region is where this charge exchange goes on, which is called generation recombination mechanism, where the different charges, the positive and the negative, are exchanged. And that's what's going on in the semiconductor. And my hypothesis is that's what's going on here in this region. Now let's drill down on this a little more. Over here, let's start with, we have our Tic Tac. And then here we have our dark torus shaped balloon. Let's go back to that and look at that balloon. Watch it. It's rotating counterclockwise. Now, we also, so we have under the house, what's happening here? Under House hypothesis, this is expanded space-time. This is what I call Boyd's anti-gravity balloon. It's the P side of the gravity diode. These dark regions to the left of the UAP, the expanded space-time, P side. Then there's this small, it's just kind of interesting, there's this little oval shaped thing that appears to be rotating clockwise below the UAP, but it's dark, so that makes it the P side. And then here's this balloon-shaped brighter region with moving darker regions to the right and under the UAP is warmer on the IR sensor and appears as a, what I said, generation recombination region. And then the balloon-shaped brighter region to the right of the UAP is warmer on the IR sensor. And this is under Puthoff's hypothesis is the denser or the end side of the gravity diode. Now, this next slide is Tic Tac space-time warp drive special relativity effects. Exactly. So above the UAP is the anti-gravity balloon. The left of the image is where a wormhole is open. And on the right side is where the UAP is space-time engineering what I call gravitational bow, like a bow and arrow, where the UAP is the arrow. And the video shows the arrow being released. That's the warp drive. So also notice, I notice that mag here is 1 throughout this. And when the thing at one point that balloon disappears, and we'll drill down on that a little more later. So now let's talk about some of these special relativity features. Now I noticed that this Tic Tac wasn't going straight. It looked like it was going like spinning like this. And that's what I'm representing here to show that it's somehow using angular velocity to create this expanded space-time situation where time shrinks and length dilates. You can see you can see over here how small it is. And then look at how its shapes change depending on the direction. So like when it starts to turn around, it looks like it shrinks again. And then here it looks like it's almost twice as long. So I believe those are special relativity effects that we're observing. And it's using the fact that angular velocity, omega, this is little omega, is not constant using this loop-de-loop. there's an angular acceleration in which the angular velocity changes. In the equation form, angular acceleration is expressed as alpha equals delta omega over delta t, where delta omega is the change in angular velocity and delta t is the change in time. If omega increases, then alpha, or the angular acceleration, is positive. So it's using this loop-de-loop to create a positive acceleration. Now I'm going to drill down. Basically what I have here is little individual slides. And I'll go through this pretty quick, but here we have dark torus-shaped balloon rotating counterclockwise above the UAP, dark region to the left of the UAP, small dark oval-shaped balloons rotating to the right below the UAP. Basically those same things we saw before. Here's another one. You notice these changes. You can see the rotation there. It's still. Now, the dark torus-shaped balloon above the UAP disappeared. UAP appears to be moving at a high rate of speed. Look at how that shape changed. It looks like it's spinning around. And then, right after that, the IR detector array appears to be saturated by heating the detector array fan out. The detector sits on this metal mesh, let's say. That's called the fan out. And somehow that's getting hot. And so the detector saturates. But the odd thing is it's in a cryogenic vacuum chamber and it's cooled. So how does it get in there? Then right after that, it disappears from the sensor, it goes black. And then we start to see that it appears again, but look at how shrunken it is. It's like tiny. And notice that how the background's kind of saturated, kind of like it's trying to cloak itself so it won't be seen. Again, next one, still there. Notice the mag change. It's 2x now. 2x. It moved over. Now it's moved to left and up. But notice it's like it's trying to avoid being detected. And then again, and now you notice that the lock from the sensor detector, that's what those little hatches are. And it shrinks again, gets more saturated. Keeps doing this for a while, for several frames. Now, it starts to look like it's moving really fast again, and it shrank. In the balloon, the anti-gravity, notice these features are showing up with the balloon and it's like it's getting ready to fire up the thrusters or something. And then it goes black, changes, and then it goes totally black. And now it's coming back. Now let's go back up to that one. Look at how small that is. Now it's almost like it's faced towards us, and then it turns. And now this is where it starts to go into this loop-de-loop thing that I was telling you about. And now watch, it's doing something. And now it takes off like that. So now this is another odd thing I captured. The Tic Tac seems to be hitting a EMP, sending an electromotive pulse. It hit the aircraft, and it saturates the IR detector array. And you can see that. So now that's my presentation. Only thing I was going to show you guys is what my next step is with this. Is I have a 5th patent that has been published, and I'm waiting to get granted to use my invention for what I call quantum gravity cryptography. And what you have here, this little image shows your hard drive has this region in the center where your disk, the head slider, sits when you're not using it. It's called the landing zone. And it has these little nanobumps that are made with the laser. And so what this device does is it uses that landing zone to create an immutable key, what's called a private key, public key pair. And so basically this is what it does. The key pair requests by the system. A map is made of the hard disk texture zone. The map data is split up into sections. A single section is arbitrarily selected. A public key is derived in an algorithm. A public key is available for use. The location of the private key is stored in memory. The public key is used for access requests. The algorithm for deriving the public key is applied in reverse. The private key location is loaded from memory. The hard disk texture at the private key location is read by the gravitomagnetic sensor for the private key. Do they match? Output of not authenticated if they don't, output of authenticated if they do. And that's it. Now, I did notice a little chatter about Dr. Tajmar, and I wanted to share some of my communications with Dr. Tajmar, starting with this first one, where I basically tell him how much I appreciate his work, and mention that basically it's mentioned in my patent on page 1 and 2. And he was very, I would say, he didn't necessarily think what I was doing was what he was doing, but he was very supportive, and I have a lot of respect for him. So I just thought you guys might want to see this. Just spend a couple minutes. I'm explaining to him how things work. Like I just told you now with the landing zone. I explained that. Basically, he was asking how I knew it wasn't electromagnetism. Is one of the reasons I knew is because I could measure it from nanobumps made of glass. Essentially, glass. That's what's different. It's not electromagnetic. It's a actual physical property of the presence or absence of matter. And like here, I shared with him some data from, this is like what texture zone image looks like, 50x, 2000x. And he was asking me if it was a chasm, what do you call it? The vacuum energy, sort of like Hal thinks it's the vacuum energy. But I asked Hal about, well, does the vacuum have a band gap like a semiconductor? And he didn't think it did. So I mean, obviously we can't agree on everything. It's by disagreeing that we figure out what's actually going on. So, and so, and the last but not least is questions and answers. And so I basically, part of my belief in nonviolence is, basically we're all seekers of truth. We're seeking to find out the truth, and that's That's a dialogue, not a debate. A debate, you know, is one where opposing arguments are put forward, and it's more important to be seen as correct than finding the truth. And so I'm looking for finding the truth, and I need all the help I can get. I don't think I got any monopoly on the truth, that's for sure. And now let's leave it with that. I look forward to your questions.
Well, Michael, thank you. And so let me do this, actually. Let me mute you out really quick. And what I'm going to do is put it on gallery view. And everyone, please give Michael Boyd a giant hand. Thank you, sir. That was an enormous and remarkable presentation. I know you've done parts of that before, so